In the previous video, we covered the first law of thermodynamics, or the conservation of energy. That video showed us that we, in fact, get out what we put into a system. Or you could say that technically we can break even in terms of the transferring energy and changing energy from one form to another. Now, the second law of thermodynamics, which also dictates how energy moves within the universe, it states that the entropy of the universe is constantly increasing. And entropy can be viewed as a measure of disorder. So entropy has other ways of being defined, but I think for our purposes, I think disorder is an appropriate way to look at the values and sign convention that we'll cover in this video. And so when you think about this, that the universe is constantly becoming more disordered, and that is just a natural law of the universe. So that is going to become a part of every process within the universe, no matter how small. Just one chemical reaction needs to obey the laws of the universe, meaning that in that reaction, the entropy of the universe needs to increase. And so because of this, you can say that when we change energy from one form to another, actually we will not break even like the first law states. The second law says that we will always lose, and we always do lose when we transfer one type of energy to another. And you guys realize that. That's what energy efficiency is all about. You can't take the reaction going on in the Humboldt Bay power plant burning natural gas and get all of that energy turned to electricity and delivered to a home without some cost, without losing. Why do we lose? We lose because of entropy. Entropy is just a part of nature, and in all of these processes that we try to produce work, we're going to lose some of that energy, that internal energy, as heat. And heat goes into the surroundings and helps the universe become more disordered. We'll get to that later. So when we look at the equation for entropy and the second law of thermodynamics, this is what we find, is that for a spontaneous change, and what I mean by spontaneous is something that actually occurs in nature, in our world, it must follow this law, where the change in the entropy of the system plus the change in the entropy of the surroundings is equal to the change in entropy of the universe, and that value needs to be greater than zero. It has to be greater than zero. Otherwise, it just won't happen. And so delta S, system or surroundings, if it's positive, it can be more disordered. And if it's negative, it's less disordered. We're not going to use the word ordered. That gets too confusing. It'll always be more disordered, positive, less disordered, negative. Okay, so we understand that this variable, delta S universe, must be positive. Well, that still gives us flexibility. The net delta S just needs to have a positive sign. So that means that delta S, it can be negative or positive. We're usually most interested in delta S because, of course, that's the part of the universe that we're studying. And so it can be positive or negative. And that's what makes entropy somewhat confusing to people, because they think that the world is just becoming more disordered. But in fact, a system can become more, I should say, less disordered. A system can become less disordered, but the cost is that delta S surroundings must become much, much more disordered. So it's a balance between the system and the surroundings. Delta S surroundings is defined as the heat gained or released by the system, and that's the negative value of delta H system, divided by the temperature of the surroundings. So that's what will define delta S surroundings. And so surroundings is definitely affected by what's going on in the system. And just note quickly, if we can look at this, so this is a negative delta H system. Temperature is always going to be positive because we're working in units of Kelvin. So you can imagine if the system has an enthalpy value that is exothermic, negative, so it's releasing heat to the surroundings, then you can see that a negative delta H and a negative of a negative delta H will give us a positive delta S surroundings. So releasing heat to the surroundings creates disorder in those surroundings and will benefit the process in terms of delta S universe being positive and spontaneous. And so again, we do need to consider our sign convention, and we need to consider the magnitude of both the entropy in the system and surroundings. So as mentioned, I feel that knowing your sign convention is one of the main take-home messages from these videos. And so let's practice some of that sign convention. So given these chemical processes, let's determine what the sign of delta S and delta H are for them. So melting a solid. So think about in terms of, is the system gaining or losing heat? And also, is the system becoming less or more disordered? And so you can pause the video, think about it. I'll show you the answers. And so let's start going through these different processes. Again, pause the video as you need to think about each of these. So melting a solid. Well, melting a solid, in order to melt a solid, you have to put energy into the system. The system is the solid. And so it's definitely an endothermic process. Also, going from a solid to a liquid is much more disordered than a solid. So we would say that it's becoming more disordered, and it's an endothermic process. Freezing a liquid, well, in freezing a liquid, we can say that it's becoming less disordered because it's going from a liquid to a solid. It has more structure, more organization as a solid than a liquid. So the sign of delta S would be negative. And to freeze a liquid, you actually have to remove heat from the system. So it's an exothermic process, and that would be a minus sign. This reaction here of hydrogen reacting with oxygen to make water, I have two gaseous compounds as reactants, and I have water as a liquid being the product. So this is an explosion. Perhaps you've seen the explosion of a balloon containing hydrogen, but it explodes. And so what do you consider occurred during this reaction? Did the disorder increase or decrease? And was it endothermic or exothermic reaction? So first, with the disorder, we're going from a gas to a liquid. So in doing so, we are becoming less disordered. Gases are very random, very disordered relative to a condensed matter like a liquid or a solid. And then this is an explosion. Did it gain or lose heat? Well, it definitely lost heat, gave off a lot of energy. A combustion reaction, and this goes for all combustion reactions, any fossil fuel. This is where we have methanol as a liquid reacting with oxygen gas, going to CO2 and water. I expect you in this class to be able to write any combustion reaction and balance it. So here we have gases on both sides. So it's somewhat difficult to know whether the phase, the state of matter, actually helps us determine whether we become more disordered or less disordered. In a problem like this, I think what's important is to look at the moles of gas and the moles of reactants. So the more moles you have, the more particles you have, the more disorder you're going to have in the system. So for the reactants, we have 2 moles of liquid, we have 3 moles of gas, but on the reactants, or excuse me, on the product side, we have 6 moles of gas. So during this reaction is driven by the fact that we create more disorder by creating 6 moles of gas as a product. So we give it a positive sign. And all combustion reactions are exothermic. They release heat. We burn fossil fuels to get that energy from the chemical bonds. And so it's a negative sign. This last one, I just want you to think about in terms of a physical process which occurs in nature and is a part of entropy and actually making certain processes spontaneous, is this idea of mixing. If you mix 2 things together, if you have 2 pure types of solvents of some sort and you mix them together, does that create more disorder or less disorder? Or if you mix river water with ocean water, 2 different types of water, what is going to happen? Is that mixing a spontaneous process? And it is, because mixing increases the disorder within the system. So look at these examples. You should be able to do the sign convention of any process that I give you.